Hello, welcome to another video of thermodynamics. In this video, I'm going to explain the first law of thermodynamics. First, we're going to talk about the general outline of the uh, first law of thermodynamics, a general uh, equation. Then we're going to derive a specific equation for closed system, and also talk about boundary work. Then we're going to look at what specific heats are, and then we derive some equations that particularly useful for ideal gases. We'll be working out two problems, problem 1 and 2, but I'm going to post these solution videos separately. Uh, then we'll look at the first law of thermodynamics for open systems, and we'll go ahead and discuss another problem. First law of thermodynamics is generally considered as a energy conservation principle. So let's assume that there's a system at a particular state named state 1, and during a process the state of the system changed. That means the properties of the system change. Energy being a property considered E1 at state 1 and E2 at state 2, two different energies. And the change of energy of the system is named as delta E. So the energy of a system at a particular state consists of three different energies. U1, that is internal energy. U is internal energy. And then we have KE1, that is kinetic energy. And then we have PE1, which is potential energy. And accordingly, at the state 2, we have U1, U2 internal energy plus KE2, that's also internal energy, plus PE2 internal energy, potential energy. So if you want to find the energy difference or energy change during the process, change of energy equal to energy in minus energy out. To find energy in and energy out, we need to know what the energy transfer mechanisms are. There are three energy transfer mechanisms we looking at here. Mechanisms of energy transfer. The first one here is heat work, the second one, and mass. So we denote heat by Q, work by W, and mass energy is E mass. So if you want to find uh, energy change, so according to this equation, change of energy, energy in minus energy out, change of energy is, so I'm going to write down this equation in mathematical form. Sorry, delta E equals E in minus E out. E in minus E out. Now delta E is delta U internal energy change, that is U2 minus U1 plus delta KE plus delta PE. And then E in, there are three different ways that you can input energy, right? Q in plus W in plus E mass in. And energy out is Q out plus W out plus E mass out. And here I can group the same energy transfer mechanisms together, and I can write Q in minus Q out plus W in minus W out plus E mass in minus E mass out. This is delta U plus delta KE plus delta PE. Now internal energy is all the energies such as kinetic and potential energies of the molecular level and other molecular level energies, all are lumped into internal energy. Kinetic energy is the energy possessed the system uh, because due to the motion, and potential energy is the energy of the system due to its position. So system can possess energy, but system cannot possess heat, work, or energy flow due to the mass. What heat and work can do is they can transfer energy in and out of the system, right? They can transfer energy to the system and transfer from the system, but they cannot stay inside the system. The kinetic and potential and the internal energies are the ones that store in the system. So this is actually this is the concise version of the first law of thermodynamics mathematically, and this is the uh, elaborated mathematical equation with all the energy transfer mechanisms written in here. So now in the next few steps, we're going to look at how we're going to change this equation A, to different uh, types of systems. Let's take that general equation. Let me change the color. Delta U plus delta KE plus delta PE equals Q in, right? Q in, okay? Q in minus Q out plus W in minus W out plus E mass in minus E mass out. This is the general equation. For a closed system, the system and surroundings is separated by the system boundary, and it can interact with the surroundings by exchanging heat, exchanging work, transferring in and out work and heat, but it doesn't allow mass energy exchange. So E mass is not allowed. because it's a closed system. The boundaries are closed. So there's no mass flow into the in and out of the system. So this term, the last term of the right-hand side of the equation is no longer valid for a closed system. So we're gonna simplify this equation. Delta U plus delta KE plus delta PE equals Q in minus Q out plus W in minus W out. And also most of the systems are not moving. When the system is not moving, we can say that delta KE equals 0, delta PE equals 0. This is most of the time this is the case. So then we can reduce the equation to delta U equals Q in minus Q out plus W in minus W out. Now, from the early developments of the thermodynamics, classical thermodynamics, engineers and the scientists were interested in looking at how much of heat is supplied to unit work output, how much of heat required to generate unit work output. So they were interested in net heat input and net work output. Okay. So we can simplify further this equation. Say, let's keep this term Q in minus Q out. And I take minus sign out of this parenthesis and write W out minus W in. So this basically represents a net heat in. So we have Q net in. Whatever the in minus out is a net input, net heat input. Minus this term represents W net out equal to delta U. So this is the most simplified version of the first law of thermodynamics for a closed system. So it's basically Q net in minus W net out. So here's the thing. Now, whenever you use this equation here, you can use this equation as well without any problem. But you use this equation, you have to keep in mind that whatever the energy or the work, leave the system is positive, right? If you say that you get a 500 kilojoule of work output, that means you put that just the number here. You don't worry about the sign. But if any system consumes work or work input, then you have to remember that there was a negative sign into that dot in, so that net output is negative now. If you only have a heat net work input, the net output is negative. So you need to put the negative value. As for the heat input, like if you consider a system, the sign convention is for heat, Q, input is positive and output is negative. For work, input is negative, output is positive. So this net out, okay? And this net in. So when you solve this equation and you get a negative value for work, that means that is a work input, okay? This will be clarified when you work with more problems. So if this is confusing, please ask questions. And also you can remember this equation where you don't want to keep uh, keep this in memory, and you just need to plug in the values of Q in, Q out, W in, W out. Whatever the equation that you use it correctly, and understand the meaning of it. And you don't want really to remember how it is derived, but you just need to understand the meaning of each and every term and the limitations of that equation. That's for the closed system. And another thing that we're going to talk about is the boundary work. The boundary work is associated with closed systems that has moving boundaries, like in piston cylinder device. So boundary work basically is taken by, it can be defined for a quasi static expansions or compressions. So this is actually reversible work input output. So boundary work 1 to 2, state 1 to 2 is integral 1 to 2 P dV. Now to compute the boundary work by using this equation, we must know the the relationship between P and V for a particular process. The simplest such a process is isobaric process. Isobaric process is basically P constant process. So in this case, your pressure stays constant. So you have, if you draw PV diagram for that process, just the pressure is constant. P at P naught, pressure is constant at P naught. And the volume changes from V1 to V2, right? And if you find the boundary work 1 to 2, boundary 1 to 2 P dV, you can put the constant pressure P naught 1 to 2 dV is equal to P naught V2 minus V1 to 1 to 2. That's for a isobaric process, or P constant pressure process. And second case is the constant temperature process of an ideal gas. Please remember that this is not true for any other substance. It's just constant temperature process. So isothermal process of an ideal gas. Constant temperature is also known as isothermal process of an ideal gas. So if you have an isothermal process of an ideal gas, you know that ideal gas equation PV equals mRT. This is pressure, total volume, mass of the system, and R is the gas constant, T is temperature. Okay, P pressure, total volume, mass, gas constant, and temperature. Okay, so, and we also know that specific volume, simple V or small v, is equal to V over M, total volume divided by mass. So we can do the same here, and then we can write PV equals RT. And now we can obtain that P is equal to RT over V. Now that's a relationship between pressure and volume. And I'm going to substitute this equation 1, W1 to 2, constant temperature process of an ideal gas. So that means for a constant pressure process, I can write for that for isothermal process. Why do we see that this equation, this derivation is only for ideal gas? Because we use ideal gas relation. Okay, this is ideal gas relation that can only be used for ideal gas. So we can write isothermal process P is equal to RT naught divided by V. Temperature is a constant T naught value. And I can write W1 to 2, 1 to 2. Instead of P, I can write RT naught over V dV. And W12 is equal to RT naught integral 1 to 2 dV over V. So this can be written as RT naught natural log of V2 over V1. So that's our equation for isothermal process of an ideal gas. Okay. And there's another process that we can discuss, and then you also discuss that in the thermo 1. So I'm not going to derive that equation. I just show you few steps. That's for polytropic process. Polytropic if you have the polytropic relation is PV to the power n equals C, where n is not equal to 1, right? N is not equal to 1. Now, polytropic process this can be true for any substance, polytropic process. This gives us a relationship between P and V. So if you consider that system changes from state 1 to state 2, so here temperature is pressure is P1, volume is V1, and you have pressure is P2, volume is V2. That'll give us P1 V1 to the n equals C and P2 V2 to the power n equals C, right? Both equal to C, because that is a polytropic process and state temperature, pressures and properties should comply with that equation. And now if you want to find W12, you can integrate 1 to 2, right? P dV, instead of P, I can put C divided by V to the power n dV, right? C divided by V to the power n dV, 1 to 2. And that I'll get C out of that equation, dV to the power n, 1 to 2. When you integrate that, you get 1 minus n C times V2 1 minus n minus V1 1 minus n. And instead of C, you can substitute P2 V2 in the first term and second term P1 V1, and using exponential rules, I can get 1 minus n, and then here P2 V2 minus P1 V1. So we're going to end up with this W12, right? So that's the equation for polytropic process for boundary work. Constant pressure process, isothermal process of an ideal gas, and then we have polytropic process. three different processes. We discussed how to find the boundary work by using this equation. So you should be able to find for any process like this if you know what the relationship between P and V. One last thing about the boundary work is the area under PV curve. So if you have a PV curve, if you know the PV curve of the process, right? That area under PV curve, this is the PV curve. Area under PV curve can be found by integration. So if you say get a little strip like this, that's dV. And here the function value of P is P. So area from 1 to 2, let's say this is A, B, C, D. This is state 1 to state 2, right? So area A, B, C, D equals integral, right? We can integrate P dV 1 to 2, which is nothing but the work 1 to 2. So area enclosed or area under PV curve is equal to boundary work is equal to boundary work. Okay. That's all about the boundary work. And if you want to discuss specific heats, CV is specific heat at constant volume, specific heat at constant pressure, CP. And these are properties, and I can show you how to derive these equations, but I'm not going to do it right now. If you need further information, please contact me and ask. But it is not necessary for you to know the derivations, but it is good to know whenever you get stuck with some problems, you need to have a clear idea about what those quantities are. So these are properties, and these are available for you in tables, and it's easy in that way. It is easier to find them. And for ideal gases, there are some other rules that we use. This is ideal gas equation. We used it earlier. And internal energy is only a function of temperature. And we also know that enthalpy is internal energy plus the flow work, PV. And also, since for an ideal gas, I can substitute PV by RT. Since U also a function of T, RT anyway is a function of T, then H is a function of T for an ideal gas. And we obtain that CV is du over dt for constant volume. And since U is a function of T for ideal gas, CV is also a function of T. So we have du is CV dt. And dH in the same manner, Cp dt for ideal gas. And from the equation of enthalpy, we can say that dH is du plus R dt. And also there's another quantity called specific heat ratio, which is K, that is Cp over Cv. Okay, these are the quantities that we need to know for boundary work and ideal gas. And we have one problem for constant closed systems. Example problem 1, let's talk about PCD, piston cylinder device. Contains steam initially at 1 megapascal and 450 degrees Celsius, and the volume is 2.5 cubic meters. Steam is allowed to cool at constant pressure until it first starts condensing. Okay. Show the process on PV diagram with respect to saturation lines find the mass of the steam, determine the final temperature, find the amount of heat transfer. So that's the question. And we have second problem, again a piston cylinder device, mass of 3 kg of saturated liquid vapor mixture of water is contained in a piston cylinder device at 160 kilopascal. Initially 1 kilogram of water is in the liquid phase and the reset is in the rest is in the uh, vapor phase. Okay, should be rest is in the vapor phase. Heat is now transferred to the water and the piston, which is resting on a set of stops, uh, starts moving when the pressure inside reaches 500 kPa. Heat transfer continues until the total volume increases by 20%. Draw a suitable property diagram to denote all these states on the diagram and the diagram. Determine initial and final temperatures, the mass of liquid water when the piston first starts moving, the work done during the process. So that's the second problem. I will post solutions or the videos for these two problems separately. Let's talk about how to get equation for open systems or control volumes. Now, our basic equation for first law of thermodynamics is delta E equals E in minus E out. And usually for open systems or control volumes, you know that mass is allowed to cross the system either at two locations or maybe multiple locations. Therefore, we are interested in the rate equation. So to find the rate equation, we have to get the time derivative of this equation. So find that dE over dt was d over E in over dt minus d over E out over dt. So this can be written as E dot in. The dot denotes the time derivative, E dot out. And we have dE over dt, rate of change of energy. For steady state systems, dE over dt equals 0 because time derivatives of properties is going to be 0. So we have E 0 equals E dot in minus E dot out. Similar to closed systems, the mechanisms of energy transfer are still heat, work, and mass. So in this case, mass is also crossing the boundary. So energy transfer takes place when the mass crosses the boundary. So here 0 equals Q dot in minus Q dot out, okay, plus W dot in minus W dot out, plus E mass dot in minus E mass dot out. So we already know what this Q in and Q out are, but E mass in. So E dot mass in equals to m dot in specific energy of flowing fluid. So specific energy of a flowing fluid can be written as U plus half V squared plus uh, GC, right? In, and it can be also written to out in the same manner. And the other thing that we need to uh, consider is the flow work. Flow work is something that the flow does on the system or system does on the flow. So let's say you have a control volume marked by this boundary. When flow enters the system, uh, I would like to get an example uh, of a packed room of people. So if you have a packed room of people, if you want to enter that room, you have to squeeze through and push other people really hard, and that means you have to work against the system. The consider you are the flow that enter into system, and the other people are the eh, flow the molecules of the fluid or anything inside the system. So you have to really work hard to get in there. So that means the flow has to work on the system. Now let's assume that somebody wants to come out of the room, right? Probably the people who are at the door will push him out, really happily get rid of him. So that is system does work on the flow. So this work can be calculated by multiplying pressure and specific volume times the mass flow rate, right? Pressure, specific volume, mass flow rate. And here also it is P M, M dot PV. So this is out, this is in. So in is work input, out is a work output. So that can also be added, should also be added to this equation. So because of the flow, then the equation looks like 0 Q dot in minus Q dot out plus W dot in minus W dot out. And then you have M dot in, right? And you have U plus half V squared plus GC in minus M dot out U plus half V squared plus GC out. And you have also flow work. Flow work is uh, work does on the system, right? Work does on the system. That means M dot PV in, it is positive because that's something that you've done on the system, and then by the system minus M dot PV PV out. And with that, we have 0 equals Q dot in minus Q dot out plus W dot in minus W dot out plus M dot in U, and I take PV into that, PV plus half V squared plus GC, everything in, right? Minus M dot out U plus PV plus half V squared plus GC out. And then you have 0 equals, this can be taken as Q dot net in, right? And this can be taken as minus W dot net out, as we discussed in core systems. And then this is Q dot net in minus W dot net out plus M dot in PUV, U plus PV is H. So you have H plus half V squared plus GC in minus M dot out H plus half V squared plus GC out. Okay, so that's your closed system equation. So you have multiple inlets and outlet. You can put sigma to add all the inputs and outputs. If you have a single input and output 1 and 2, like in this case 1 and 2, you can further simplify this. Mostly we look at single input output devices. So you have Q dot net in minus W dot net out plus, let's say one is inlet M1 H1 plus half V1 squared plus GC1 minus M dot 2 H2 plus half V2 squared plus GC2 equals 0. And this equation is single input, single output device, single stream device. Otherwise, can we use this equation in red? So that's all about open systems equation. So first we have the general description, the general notation of the first law of thermodynamics. Then we talk about the rate, and from the rate equation we got the steady system and steady state system. So this is only true for steady state system. Then we substitute for mass energy, and then we look at the flow work, and then all these things come together, come into this steady flow energy equation. You use this over and over again in thermodynamics too. Okay, please do understand what the terms and what each and every thing mean in this equation. So we're going to work out a problem based on that first law of thermodynamics as well. Please go through the problem and post the video and go through the problem and try to work it out. I'll post the solutions in a different video so that you can look over if you get any difficult points in this problem. All right, so that's the end of this presentation, and hope to see you in another video. Thank you very much.